Hello and welcome back to Biology Decrypted. I hope you're doing well, and we are continuing our English series on biochemistry, that is Biochemistry Decrypted, and this is lecture number 8, that is Ramachandran Plot. If you haven't watched the previous lectures yet, well, you will be finding this in the I button in this playlist, and you can watch all the lectures, all the previous lectures, and then come back to this one. Starting Ramachandran Plot. Well, before this, we need to revise the peptide bond. We had actually, I had left you at a cliffhanger in the previous lecture. We'll be continuing from there. Well, what we know is we have this thing called the peptide bond. Yes. Now, how does it form? We had already seen it. How does this formation take place? The peptide bond is formed in this manner. There is this amino acid number 1 and it has a C double bond OH group attached to it. And then there is this amino acid number 2 and then this has NH2 group attached to it. Then water is removed from here. From here, water is removed, and then finally, what we see is, after the removal of water, the bond which formed is the peptide bond. This is amino acid 1, CONH, amino acid number 2. This bond is called as the peptide bond. Now, if we look at the structure of the peptide bond, which I had already shown in the previous lecture, we'll revisit it again. Coming to the structure of the peptide bond, if we see, we have this alpha carbon, to which we have this CO, and then we have NH, and then we have C alpha, and then again there is this bond. This is how it continues. Obviously, the C alpha will be attached to R group. It will also be attached to H. It will be attached to H and R, obviously its own R groups. Now, if we try to look at this particular carbon, if you actually look at this particular carbon like this is the carbonyl carbon. This carbon is known as the carbonyl carbon, or we can call it as the carbonyl group. This is the carbonyl group. Now what happens is, obviously here one bond is pi bond, the other bond is sigma bond. These pi electrons, they have a unique property of delocalization. What they can do is, these bonds, if present in this manner, if there is a sigma bond, pi bond, and then there is another sigma bond, what we can say is, if there is a charge here, or if, let's say, if there is a lone pair here, there will be a tendency in which this lone pair will become a pi bond, and these pi bonds will come to this atom, and this is how resonance will take place. This is how resonance will take place. And there is another carbon here, and here what happens is lone pair with a negative charge, and here we get a double bond. Well, this is known as delocalization, and this leads to the phenomenon of resonance, and this is how resonance structures are formed. So what we see here is that in this carbonyl group, since we have carbon as slightly delta positive and oxygen as slightly delta negative, what we can say is these pi electrons will go on oxygen, and simultaneously, since this nitrogen has a lone pair, this lone pair will be coming here. This lone pair will be coming here, and since nitrogen is giving its lone pair, and therefore it will have a positive charge. So what we can see here is the resonance structure will be like this: C alpha, there is R, there is H, this is connected to C, O, and this is how you get lone pair with negative charge on oxygen. And then you see that this is N plus H C alpha, like this. So this is how you get two different, these are the two resonance structures. These are the resonance structures, as we can see. Now this carbon as well as the oxygen, the hybridization of this is sp2. Hybridization is sp2, and sp2 hybridization represents a planar structure. It actually represents a planar structure, specifically trigonal planar. trigonal planar, or simply you can call it as planar, which means the structure lies on a plane. If you take this example, if you can see it here, so this is something sort of a plane. This is a planar structure, as you can see here. This is a planar structure. This is one simple sheet or one simple plane. This is how the carbonyl carbon is arranged. This is how it is arranged. So obviously they will be in a plane. If you look at the bond, there is this carbon oxygen bond like this. This is the sigma bond, and here you have the vacant p orbitals which actually form the pi bond like this. This is how they undergo sideways overlap, and this is how the pi bond is formed. So this is how we write pi bond. Now these resonance structures in general, they have a resonance hybrid. And if you look at the resonance hybrid here, this will be C alpha R H, then we have CO, then we have, so what we can see is these electrons are coming here, they are forming a double bond, a pi bond, and these pi electrons are going and coming on oxygen. This is how you get the electrons here, and you get this and this here. So what you can see is the electrons can come back like this, and it is delocalizing on these two centers. Like these three centers are involved, and this is how you can say that there is a partial double bond character. Like this double bond is not purely a double bond, it has some single bond character, or you can say this single bond is not a pure single bond, it has a double bond character. Partial double bond character is something what we can see here in case of peptide bonds. So the CN bond strength will definitely increase because of this partial double bond character. So this is how we can make the resonance hybrid. We can draw the resonance hybrid like this. There will be CN H C alpha R H like this. This is the resonance hybrid, as you can see. And let me tell you that resonance structures are imaginary structures that are proposed structures, but resonance hybrid is the actual structure that exists because it is happening dynamically. This whole thing is happening dynamically, and this is how this whole phenomenon of resonance occurs. And peptide bond, due to resonance, it shows a partial double bond character. So the CN bond shows a partial double bond character. Now let's move forward. Here I have included some diagrams which will help you visualize this process, what is happening actually here. So if you look here, initially the electrons were present here, the lone pair was present here. What happened is this delocalized, and what happened is these electrons, actually these were pulled on this oxygen. So oxygen then will have, finally it will have a lone pair with a negative charge, and this will undergo pi bond formation with this, and since it is giving its own electrons, so it will have a net positive charge. This is the thing that is happening. The steps that are happening in this first scenario, what we can see here is the lone pairs on nitrogen go here, and then this goes here, and as a result this is the overall orbital picture. As you can see, this is on a plane. All these atoms are on a plane because this carbon has sp2 hybridization. So this is the orbital picture that we can represent, and also this is the first structure. Moving forward, if we look at this one, this is the second structure. Now as a result, after this, these electrons got delocalized. What you see here is nitrogen develops a positive charge. Obviously this nitrogen has a positive charge now, although it is having a pi bond, a newly formed pi bond with carbon, but still it has a positive charge. And oxygen with its electrons, it has its electrons, and overall it has a net negative charge. So this is again the orbital picture. Now moving forward, you can see the different orbital pictures. Moving forward, what you can see here is this. This is actually the structure of the resonance hybrid. This is the resonance hybrid, and what we can see here is this is getting delocalized. This is how you can draw it in a dotted manner, and this is how the electrons are going from here to here and here to here, and this is how they are doing resonance. And this is how you can see that the electron cloud is delocalized over these three centers, and this leads to stability. Obviously this leads to stability because charge is not concentrated on a particular atom, rather it is distributed among few atoms, and this is how this leads to stability. But although it leads to stability, what we are concerned with is the angles. I'll introduce you to the dihedral angles concept. Well, then you will get to know that although it introduces stability, but this actually brings in new restrictions. And one of the restrictions we'll be talking about here, the major restriction that happens here, is this restriction due to the presence of partial double bond character. Also, if the R groups are bulky, even then there will be some restricted angles. But yes, this is the major factor. Now, talking about resonance, when we talk about resonance, actually because of the phenomenon of resonance contributes to approximately 40% double bond character. So what we can say is this particular bond is the CONH bond, the peptide bond, has a 40% double bond character. And as you can see here, you had already seen the structures that CO partial negative, NH partial positive, like this. What you can see here is this has a partial double bond character. And because of this partial double bond character, what you can see here is a single bond. This is a sigma bond. This is a simple sigma bond. Now, what we do is, if we have a weak pi bond on top of it, this is like a pi bond. Now, what we can say here is, this could have rotated. There could have been infinitely many possible rotations. But when we introduce a double bond here, even if it is a partial double bond, even if it's not a complete double bond, what you can see here is there will be a restriction in the rotation. This won't be rotating as freely as it could if it were a single bond. So because of this introduction of a partial bond, double bond character, there comes this restricted rotation. So because of partial double bond character, your peptide bond shows restricted rotation. Now, let's look at the structural parameters of the peptide bond. Well, now, here we have the peptide bond. This is your peptide bond. And here we have the structural parameters. If we talk about the structural parameters of the peptide bond, we can see here that the carbon, alpha carbon, and this carbon, which is the carbonyl carbon, if you look at this bond has a length of 1.51 angstrom. Well, the units here are in angstroms. And 1 angstrom is equal to 10 to the power minus 10 meters. You should remember this. Now, if you see the length of the carbon oxygen bond, it is 1.24 angstrom. Carbon nitrogen bond, it is 1.33 angstrom. Nitrogen hydrogen, it is 1.0 angstroms. And here, if you see between nitrogen and the alpha carbon, it is 1.46 angstroms. Now, if you talk about the bond angles, well, it is roughly planar. That is why trigonal planar. If you actually try to divide it, divide 360 degree by 3. So what you get is 120 degree. On an average, it is 120 degree, but you can see slight variations here and there. There are slight variations here and there. It's not purely 120 degree, but yes, it is somewhat similar to 120 degree. Now, even here, you see that it is somewhat similar to, approximately it is equal to 120 degree. Since this whole thing is planar, since this whole part is planar, Therefore, the angles are approximately 120 degree, and therefore this whole thing remains on a plane. If there is a plane, if there is a sheet of paper, you can actually draw a peptide bond, and that's how you represent it. Although the other carbons, the carbons at the end, they will be having three-dimensional, they will be having this tetrahedral structure because they are having R group and H group attached to it, and also there is no kind of resonance going on there, so they will be having a tetrahedral structure. But yes, individual these units, the whole unit including the peptide bond, this whole part, this will be present in a plane. This will be present in a plane which is commonly known as, in a generic sense, in a very generic sense, when we know that peptides are amides. So this is what we'll call them. We'll be calling this as the amide plane. As you know, it's a planar structure. So if you look at this particular plane, this whole plane is known as the amide plane. This is the amide plane. And now, obviously, structure is obviously planar. This is planar. And if we try to look at this particular configuration, well, we know that when these carbon alpha and carbon alpha, this is the alpha carbon, this is the alpha carbon, and across this restricted this bond which is having restricted rotation, if you have the groups oppositely oriented to each other, for example, if you have a double bond and groups are oppositely oriented to each other, then this is transform. And if you are having this kind of an arrangement, they are on the same side, in that case you'll be calling it as cis configuration. So here what you can see is the peptide bond, here it is having a trans configuration, and here obviously trans is obviously dominant. Trans is dominant configuration, and this is relatively more stable. Like in general, for most of the amino acids, this trans configuration is very stable, and if you try to draw it, this actually represents this thing roughly. Since these are present in this opposite manner, C alpha, this is called as trans. Now, there is another configuration possible. There is another configuration possible, and this is kind of an exception, but yes, it is not that it is not completely found. It can be found. So if you talk about an exception, generally it is not found, but yes, it can be found in some cases. So this is the presence of the cis peptide bond. We have already seen this one. This is the trans peptide bond. There can be the cis arrangement as well, where if we actually try to draw it, what we can do is we can draw it CONH, and then we have sorry, this we can draw this in this way. Nitrogen can have this here, and then in this way we can make this C alpha. This actually, if you actually look at it, here you have R group, here you have H group, here you can have some other, actually you will have the next peptide bond, here you have the next peptide bond, here you have R, you have H. Actually, these R groups, in most of the cases, this can be very bulky. These groups can be very, very bulky. And if you actually try to look at the van der Waal radii, if you actually try to look at the van der Waal radii, what you can see here is this will have a van der Waal radii here, this will have it here, and obviously they will be opposite to each other, so they won't be having steric clashes, they won't be having steric hindrance. But here, if you see, this will be a big group, this will be a big chunky group, this will also be a big group, and because of this, in this area, what you can see here is the van der Waal radii of both is clashing in this part. It is actually colliding, and this results in steric hindrance. This results in steric hindrance. Now, well, is it stable for anyone? Well, for most of the amino acids, this particular configuration is not considered as stable. But if we talk about proline, for example, if this part belongs to proline, in that case, this won't be an H. If you look at the structure of proline, if you try to draw the structure of proline, you can draw it very easily. Here you have CO minus, here you have H, you have N, H2 plus, and here you have 3 carbons like this. What you can see here is this belongs to the backbone itself. This belongs to the backbone itself, and in this case there will be a strain. There will be a strain if it is in the trans configuration. So what we see here is there are like these prolines are more favorable, they are more stable in their cis configuration because of this very obvious reason, because their structure is such that if they actually have this peptide bond and if they are having their nitrogen involved in the peptide bond, they will always prefer a cis configuration over a trans one, because in that case, in case of trans, it will have a high steric hindrance. Rather in the cis one, at least there will be more amount of stability, and what we can see here is almost approximately 10% of proline residues, they are actually found in cis configuration. So approximately you can say 10% of the proline residues that are found in proteins, they are found in cis configuration, which is an exception to the general rule applicable to all other amino acids. Now moving forward, let's talk about this famous polypeptide backbone. Let's take an example of a polypeptide where you have many alpha carbons. You have many alpha carbons here. Let's say this is an alpha carbon. Then you have an alpha carbon here, and then these groups are continuing. These groups are continuing, and this is how you can draw. This is how you can draw an axis, or you can say this actually behaves as the backbone for the polypeptide. This behaves as a backbone for the polypeptide, and you can show it by this dotted line. You can say that this is the polypeptide backbone. Now, how can we show this? Like simply there is this planar structure, and then there is this alpha carbon, then again there is this planar structure, again then there is this alpha carbon, again there is this structure like this whole thing is continuing, and then there is this backbone which is present throughout. This is the backbone which is present. Now if we talk about hedron, for example, what does hedron mean? Hedron, the word itself means face, and in this case we'll be talking about different triangular faces. For example, if you remember the Newman projections, this is how Newman projections were used. For example, there is a carbon, for example there is this particular molecule, there is ethane, and you are looking at this from here. What you can see from here is this carbon is present here, the dot is present just in front of you, and the carbon which is behind, which is shown with this form of a bigger circle. And how you draw it is, since this is present exactly behind it, so you can call it as an eclipsed conformation. Because eclipsed, what does this mean? Eclipsed simply means that one is behind the other, like solar eclipse, lunar eclipse, right? So this is how you actually draw it. And how do we represent it finally? Well, this is how we represent it. This is present just behind it, and therefore this is the eclipsed conformation. This conformation is eclipsed. And there is another possible conformation where they are far away, because if you have bulky groups here, obviously these bulky groups will have a big clash, and this will be unstable. This will be unstable most of the times. And if you talk about this staggered form, what does staggered mean? Well, staggered simply means that if you have this particular carbon, the front carbon, if it is arranged in this way, obviously the other group will be present exactly opposite to each other. In this case, the angle here is 0 degree, whereas if you look at the angle here between this group and this group, the angle here is 180 degree. And since this angle is 180 degree, they are called this conformation is called as staggered conformation, and obviously this is more stable. Now What was my purpose to explain this eclipsed and staggered conformation? Well, there was a reason. If you look at this kind of a face, this is a face and this is a face, and obviously they have an angle of 0 degree. This is a triangular face and this is a triangular face, and you saw the angle difference between this point and this point. You saw that this was 180 degree. These triangular faces are called as hedron, or in plural form it is called as hedra, and based on this, since there are two triangular faces involved, the angles involved are called as dihedral angles. These are called as dihedral angles, or you can call these as rotational angles, or you can call these as torsional angles. Obviously, as they bring about torsion or strain into the system, because at some angles it may happen that they are actually in an eclipse conformation and they are unstable. Like this particular conformation is unstable and it is generally not allowed. So there comes the concept of allowed and disallowed conformations. Some conformations are favorable and they are allowed, and some are not favorable and they are disallowed. So this concept is always applicable. Now let's talk about the dihedral angles in case of peptide bonds. Well, if you see here, the one which is present between C alpha and N, the one which is present between C alpha and N, this one, the one you can see here, C alpha and N. This one is known as, well, let me show you this one. The Cn is known as phi. And then if it is between C alpha and C, this is known as psi. The one between nitrogen and carbon is known as omega, and the one between the side chain, that is the R group, and carbon is known as chi or chi. Now let's look at this particular structure. This actually represents this whole thing. Well, now if we talk about this particular structure, and if we try to draw it, if we try to represent it in a very simple manner, well, in this case we can actually show this as C alpha, then we have the carbon, then we have oxygen, the carbon and oxygen, then we have nitrogen, hydrogen, C alpha, and this C alpha is attached to a R group, and here this is also attached to its respective R group, and also this whole thing continues. Obviously there will be another N group here, this will be there, this is continuing. We are looking at this particular system, and let's just try to encircle it in this way. For example, if you are trying to make an outline here, you are trying to make an overall outline here, this is how it will look. This is how this outline will look. Now, if I talk about this particular bond, this C alpha and R bond, here obviously there is this single bond. Even here it is the same. There is this single bond, and if you try to show this single bond, the rotation about this single bond, free rotation is possible, and this particular angle is known as chi or chi. This is the angle called as chi or chi. Now if we try to show it with a different color, let's say we are talking about the C alpha and C, this particular bond, and here if you are trying to show this particular rotation, this particular angle which is possible, that is the bond present between C alpha and the carbon, there is this particular angle possible. This angle is known as psi. This is known as psi. And now if we move forward, and if we try to show the one between N and C alpha, this is this bond, and here if you try to show the angle here, this represents phi. This represents phi. So this is psi and phi. These are two main angles, that is the angles present between C alpha and C and N and C alpha respectively. And the one present here, obviously there will be a partial double bond character here. You can define a dihedral angle here as well. Well, for this one, if we talk about this particular center, we will have a bond which is denoted by omega. This is denoted by omega. I hope the angles are now clear. Now you can clearly understand which one is, this one is psi, that is between C alpha and C. Then between N and C alpha, it is phi, and then this is how you can define it. For Cn, this is omega. For C and R, this is chi or chi. As simple as that. Now, if I ask you, how many degrees of freedom exist? So, per residue, on a per residue basis, how many degrees of freedom exist? For example, if we have this particular question, our clear answer will be 2. There are 2 degrees of freedom because there are 2 such bonds per residue. Because per residue, if you see, there will be 2 such bonds which are involved, because this is an example of a residue, the C alpha, this C alpha. And now this C alpha, obviously this C alpha will be connected to us. This will have a C alpha C bond, and this will also have a CN bond, and this is how this particular bond will be known as phi. This particular will be known as psi. So this is how each residue, each alpha carbon will have this one and this one, that is 2 degrees of freedom. 2 degrees of freedom will exist in case of each residue. Now, talking about the psi and phi, well, there is a trick to remember it. There is a trick to remember psi and phi, and this has been asked in many exams previously. We're talking about psi and phi. I'll say sci-fi. You have heard about sci-fi movies, right? Science fiction. So now, if you try to write it, this is psi and this is phi. Now you can draw the symbols. Psi looks like a trident, and this is how phi looks like. Now, what will you do? You will say, well, I hope you have heard about Cartoon Network, and you can say sci-fi Cartoon Network, sci-fi on Cartoon Network, and then you can say C alpha, sci-fi Cartoon Network, C alpha, and this is how you actually complete it. And obviously you now know that here this particular bond is known as omega. This is your phi, this is your psi, and these are the different angles which are possible here. These are the dihedral angles. Now we have seen that which are the dihedral angles. Now the combination of these dihedral angles will lead to many possible formations. There will be some conformations which are feasible, which are allowed, and there will be some which won't be allowed. Now, if you actually start looking at it, obviously these structures, these particular structures, oxygen will have its own van der Waals radius. Obviously there will be another oxygen which can come here because this angle is rotating. This whole part, you can actually look at it as if this whole plane is actually rotating. This whole thing can rotate about this bond. This can go from this can go from here to here, like this. It is rotating. This is how it is rotating. You can actually consider it as fixed structures. For example, if you are taking 2 cards and there is one point, there is a connector which is connecting them. Now you are actually rotating these 2 cards about this particular point, that is this alpha carbon. These are the only degrees of freedom it has. These are the only 2 degrees of freedom it has, and because of these combinations of angles. But yes, obviously this can rotate from 0 to 360 degree. But how do we define it? Actually, we make 0 to 180 degree here, and then we make this to this here. This is defined as minus 180 degree. So from plus 180 to minus 180, which means it actually covers a total of 360 degree, that is like this. So this whole rotation is possible, but are all conformations allowed. What if this oxygen comes here? What if this oxygen comes here? If it comes close to this oxygen, their van der Waals radii will actually clash, and if they clash, obviously this won't be favorable. This won't be favorable enough. This is one thing. For example, this is coming here from here to here. This will span 180 degree. This will span 180 degree, like minus 180 degree. And now if it comes here, let's say if it comes here like this, if it comes here, then what do we call it? What will be the angles be? Here we are not moving one and we are just moving the other, let's say. So obviously psi is 0 degree here, but phi is 180 degree here, like minus 180 if it is coming from here. So yeah, sorry, the psi is not moving. Psi is 0 degree, and here if it is coming 180 degree here, then we can say that this oxygen will come close and these will actually clash. Similarly, you can try different angles. There can only be a few angles which lead to stable, possible, favorable conformations, whereas others won't lead to the favorable structures. Now we are coming to the point. Now we are finally coming to the topic, that is the concept of Ramachandran plot. What actually constituted this plot? Well, what was this plot all about? It had to do with the dihedral angles. The dihedral angles about which free rotation was possible, and this was obviously psi and phi. And this is how he plotted the values of psi and phi that led to favorable structures, and he found that on a full plot, only few regions were actually occupied by these favorable structures, and all other regions were found to be empty. Like in case of general amino acids, if we talk about some special amino acids, we'll find that there is a variation. In case of glycine, obviously the flexibility will be more, the rotational barrier will be less, because apart from the peptide bond, apart from the restricted rotation of the peptide bond, there is another factor that comes into play, and that is the presence of bulky R groups. Let's say if this R group is very bulky, in that case this will also influence the conformations. Whether the conformations will be favorable or not, this will be influenced not only by the rigidity of the peptide bond, but also because of the bulkiness of the R groups. If the R groups are bulky enough, then also we'll see that there are only a few conformations possible. Some conformations get restricted because of this steric reason, because of this steric clash that can take place. They won't be having that particular conformation. Coming to this point, what we can see here is that here phi is 0 degree and psi is 180 degree. Let's say phi is 0 and psi is 180, and what we can see here is this which initially used to be here is actually rotated this whole path, and finally it went 180 degree positive, and then it came here, and finally what we can comment here, or you can say that this was here and this rotated. Either way is possible. Well, in that case you can see that this non-bonded contact radius, this part is actually leading to a clash, and this won't form a favorable structure. Now if you see here, if you are rotating this one, for example, if you are taking phi as 180 degree and psi as 0 degree, in this case as well, you can see that this is coming from here to here. This is 180 degree, of course. Now even on this, what is happening is, this is how it is clashing. Now here, if you see, if both are at 0 degree, well, if they are not far apart, then they will come so close that this will clash even more. This is not possible. 0 0 is not possible. 180 0 is not feasible. 0 180 combination is not feasible. Well, if you look at this particular structure, if psi is 180 degree, phi is minus 60 degree, in this case they are far apart. Nothing is colliding as such. And in this case, there is no such steric clash happening. And because of this, this one is a favorable structure. So what you can say is, since there are 2 degrees of freedom, and these angles can rotate actually from 0 degree to 180 degree and then again back to 0 degree, so that is 360 degree. Although we define it as minus 180 to plus 180, but I already told you this actually spans 360 degree. There are 2 degrees of freedom. This shows full freedom theoretically. If you talk about practical conformations, well, for practical conformations, only few are favorable. So theoretically, possible conformations can be infinite, but practically only a few favorable conformations exist. Well, few with respect to the huge number of theoretically possible conformations. Those are infinite. Well, in comparison to those, there are a few. Now, why does this happen? Well, this happens because of a reason. Some of the values of phi and psi, some of the values of phi and psi are not allowed. And now you know the reason, because since these values, these combinations would have led to steric interference or steric hindrance, that is why nature has simply avoided. Well, why to keep something which will lead to instability, right? This will make it very unstable, and we don't want unstable systems. So that is why, to avoid this steric clash or steric interference, what happened is only those were preferred which led to a favorable combination and less steric interference, and these were the allowed angles. These were the allowed combination of angles. And G.N. Ramachandran, famous Indian scientist working in Madras University, he and his co-workers, of course, Dr. Ramachandran, what did he do? The main thing what he did is he actually plotted these angles. So what did he do? He took psi and phi. He took psi and phi. So you can do it in a different way as well. Well, in the general plot that we will be seeing, we'll see that here we have psi on the y-axis, phi on the x-axis. Psi on the y-axis, phi on the x-axis. So if you try to present it in a different manner, you can also do it in this way. This can be phi and psi as well. Obviously, this will get a bit reversed, but yes, the plotting can be done in both manners. If in any question it asks you to do it in this manner and it is given in this manner, don't get surprised, because yes, this is another way of representing it. The same graph, if you just rotate it and if you look at it, it will look the same. It will look like this only, like it will have phi and psi. The axis will get changed. But yes, if you go by the original plot, on the y-axis we had psi and we had phi on the x-axis. So this is how the Ramachandran plot was there, and obviously it was like a normal plot like this. This is how the graph was plotted. And what was being plotted here? Well, the combinations of psi and phi, the combination of psi and phi angles, and obviously the angles here, if you try to look here, this is 0, this is 0, this is minus 180 degree for both, this is plus 180 degree, and this is plus 180 degree. And now what he started doing is what I am doing. Started plotting all the values. Well, what he found is he found some values were accumulated here. Then what he found is then there was this particular region where again some values were concentrated. Again, then he saw that in this particular part some values were concentrated and the other parts were empty. This is how he started plotting the values. And what he saw is the empty spaces. The empty spaces represented those psi and phi values, those combinations which were sterically forbidden. We can say sterically forbidden, or you can say disallowed. These were forbidden or disallowed. And if you talk about these were the ones which were sterically allowed. And these were the ones which led to the folding of this backbone, and due to this folding of the peptide backbone, structures which were now formed were called as secondary structures, and these structures needed some stabilization. Hydrogen bonds were formed, and this is how different secondary structures were formed. This was the origin, this was the logic behind the formation of various kind of secondary structures, which we actually found distributed in proteins, which we actually find commonly distributed in proteins like alpha helices and beta pleated sheets. We'll be discussing about all these in detail, but yes, as of now you should remember that these sterically allowed conformations are the ones which are found in the proteins that exist in nature, and the sterically forbidden ones do not exist because, for obvious reason, they are actually leading to an unstable structure which cannot be afforded by nature. So this is how he showed the distribution. He showed the distribution of allowed values of psi and phi. So he showed the distribution of allowed values of psi and phi, and this is what we got as the Ramachandran plot. This is commonly known as the Ramachandran plot, and this is the Ramachandran plot which we are seeing, which you can see on the screen, is for poly L-alanine. For example, you have L amino acids. For example, this is for an L amino acid, and obviously you have a polypeptide. You have polypeptides, and there are these polymers like this. For example, continuous manner, you have alanine, 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 like this. For this, the plot was made, and this is how roughly we can draw this. It will vary for individual amino acids. It will vary slightly. It will vary for some amino acids. It will be completely different. But yes, this is how the actual Ramachandran plot looked like. So this is Ramachandran plot. Now, if we try to identify what structures can be formed, what structures can be favored by all these different values, what will this region prefer? What will these angles prefer? Because all the combination of angles are different, and these different combination of angles will lead to different folding of the backbone, and therefore different structures, different secondary structures can form. And so every point will somewhere or the other contribute to the formation of some different secondary structures. Now let's continue. Let's talk about these structures. As you can see in this diagram, let me zoom it. In this particular diagram, you can see that here you have anti-parallel beta sheet, parallel beta sheets. All these are secondary structures which we will be dealing with later on. Collagen, which is a triple helical structure. Then we have left-handed alpha helix. Also, we have right-handed alpha helix here. Then we have these ring-like structures, which is called as a pi helix. So all these structures are possible. All these secondary structures are possible, and they have their characteristic values of psi and phi angles. Now let's zoom out, and what we will see here, that we have seen the representation of all these different secondary structures on the Ramachandran plot. Now, coming to an important point. Well, what are these grid lines, or you can say what are these contour lines, as you can see here? This one, this one, this one, and what are these numbers signifying? Well, these numbers signify the number of amino acid residues present per turn. Like in every turn, how many residues are present? And this for example, if you have this positive sign and you have this negative sign, what does this signify? Well, this signifies the handedness. So this plus or minus, well, this plus or minus, this signifies the handedness. So what you saw here, +4, +5. So this, if it is positive, if it is negative. If it is positive, then it signifies a right-handed structure. Or for example, it can be a right-handed helix. So what you see here is for the left-handed helix, you have a minus sign. You have a minus sign here. And for the right-handed helix, for example, here you can see, you can find the right-handed alpha helix. Here you have +4. So this signifies that there are these many approximately amino acid residues per turn, and also this plus and minus signifies the handedness, right-handed and left-handed respectively. So the number signifies amino acid residues present per turn. Now, this is how we saw the overall distribution of the Ramachandran plot, and in the end, we will be learning how to draw it with tricks. Of course, we'll be learning to draw the Ramachandran plot. Well, now we'll move forward and we'll talk about two important amino acids. One is glycine. Well, glycine is the simplest one. There is hydrogen as a side chain. And glycine, therefore, it shows maximum conformational freedom. Because the R group is the simplest, and therefore there will be more possible allowed psi and phi angle combinations. And therefore in the Ramachandran plot, what we see, like roughly we can draw this Ramachandran plot for glycine. So here we have drawn the Ramachandran plot for glycine, and what we see here is it occupies maximum region. Like what we saw here, this general Ramachandran plot, this had this much area occupied, but if we have it for glycine, then what we see that maximum area is occupied on this Ramachandran plot. So yes, maximum area because of maximum conformational freedom in case of glycine. Now let's talk about another amino acid. Well, it's not an amino acid to be specific, it is an amino acid, proline, the only amino acid present in this group of amino acids. Well, if we try to draw the structure, it's COO minus H, NH2 plus, and then there are 3 carbons like this. If we try to draw the Ramachandran plot here, and if we try to show the allowed conformations, what we see that the distribution is present only in this particular region, this much region. And this clearly signifies that because of this structure, because of this additional steric factor that is introduced because of this particular backbone, as you can see here, that this nitrogen is not a free one, and the peptide bond that will be formed, and in most cases if there is a trans peptide bond that is formed between any other amino acid residue and proline, in that case it will have high level of steric hindrance. Therefore, some of the prolines will prefer a cis conformation, as I told you, a cis configuration over the trans configuration. But whatever the case may be, that would lead to some of the possible angles. But yes, again, overall, it won't lead to the formation of many secondary structures. It will be highly restricted, and therefore, what we can say is among all the amino acids, it has the least allowed region, and that's proline. Now, if we talk about D amino acids, let's say all these were L amino acids. Now, if we talk about D amino acids, what will the Ramachandran plot look like? Well, what you have to do is, I won't draw it for you. You have to try it yourself, but I'll give you the hint how to draw it. Whatever you have in this quadrant, and obviously, what are these quadrants known as? This is known as the upper right, upper left, lower left, and lower right. These are the quadrants, and this is how they are signified. Now, what you have to do is you have to place a mirror plane here, and whatever is present here should be mirrored here. Whatever is present here should be mirrored here. Similarly, there is another mirror plane diagonally here, Whatever you have here is presented here, and whatever you have here is presented here. That is how you get the Ramachandran plot for D amino acids. Well, if it is given for D alanine, let's say, if it is given for L alanine, for example, you have the normal Ramachandran plot for L alanine. Now, if you want to have it for D alanine, what will you do? You will draw these mirror planes, and by drawing these mirror planes, you get the reflection diagonally on, like, these will actually switch. You will be actually swapping between these two, that is upper right and lower left. So this will get swapped, and lower right and the upper left and lower right will swap, and this is how you will get the Ramachandran plot for D alanine. Try to draw it, and try to verify it, and that's how you do it for D amino acids. Now let's come to the diagram of Ramachandran plot and how to draw it, how to remember it in a very, like, through a cartoon. So let's see it once. Well, yes, this is the Ramachandran plot. Now what we see here is, this is the same one which we saw here. We have drawn the actual secondary structures which are found in specific regions, and we have drawn it in a very simplified manner. This is how you can see this part, then there is this part, then there is this part, then there is this part, and there is this part. These are the parts that we will show, and again this part is continuing. Since this part is continuing, we are drawing this like this. Now what we will see here is, if we try to replicate this and we are trying to make a cartoon, there is this Ramachandran plot here. Now what we'll do here is, we'll try to imagine a person like this, a person who has his waist here, then there is, this person is wearing a dhoti, and this is his dhoti like this. This is his leg, and then this is his shoe, this is the shoe, and you can actually keep on comparing. This is his pair of socks. This is a part of pair of socks, and therefore you can say PAIR. So this is the R part. Just remember this, and then we'll see what does this correspond to. Well, now if you see, what happened is, on his dhoti, let's say he had a pocket. And he had two different pins kept in this pocket. One pin looked like this, and the other looked like this. Well, these are the beta structures, the beta sheets, that is parallel and anti-parallel. And you know what does anti-parallel mean? In this fashion it is called anti-parallel, in this fashion it is called parallel. So yes, this one is anti-parallel and this one is parallel. So this is how it is present here. If you see, you find the anti-parallel beta sheets and the parallel beta sheets in this manner. What happened is, from his pocket, when he was actually running, this person, let's draw the person. This is the cartoon of that particular person. Yes, this person is trying to run, and what we see here is, this is the person, this is his face. Although this diagram doesn't look very realistic, but yes, it's a cartoon. We are just trying to remember things. Now what happened is, from his pocket fell his wallet, and this is the wallet. This is the wallet which fell down, and this is WALLET, wallet. So this L is the highlight here. So these were the beta structures. And now what we saw here is, the number written on his shoe was 3. The number written was 3. Here, if you see, here C was written here. There was this C letter written here. And now, if you see, we have C written here, and then we have 2 written here. Well, now it is very easy to remember. What does this L stand for? This stands for left-handed alpha helix. This stands for right-handed alpha helix. So that's how you signify this. So wallet, pair of socks. So R from pair and L from wallet. This gives you the left-handed and right-handed alpha helices respectively. And then you have this pocket where you have the two beta-shaped pins, beta-shaped, there are these two beta sheets. Obviously, one is this anti-parallel beta sheet. The other one is the parallel beta sheet. Then you have collagen here, that is, I told you, C. Then there is 2 written here that signifies 2.27 helix. And what does this mean? We'll see it in the upcoming classes. Here we have the left-handed alpha helix. Yes, and as you know the angles, this is 0 degree, and obviously here in this quadrant you have plus 90 degree, plus 180 degree. Similarly here we have minus 90 and minus 180. And similarly here we have minus 180, minus 90, 0 degree, plus 90, plus 180. And in this manner it is represented. And obviously each of these structures will correspond to some value of psi and some value of phi. And this combination is very important. Well, we'll go through a table after this where we'll be remembering these values in case if it is asked. So you can always answer by referring to this table. And you can actually after practicing you can somewhat memorize this table for some important structures at least. So here also there is this pi at the bottom of his shoe. You can see pi is written. So this is pi signifying pi helices. Then there is this alpha r which signifies a right-handed alpha helix, and 3, that is the number written on his shoe, is a 310 helix. These are the secondary structures represented in the Ramachandran plot, and this is the way to learn it. Well, now if you try to draw these 4 quadrants, what you see here is if we have different values of, here we are representing psi, here we are representing phi. Now what we see here is that psi has positive value and phi also has a positive value here. Then if we talk about this particular quadrant, psi positive, phi negative. In this one we have negative negative, and here we have negative positive. And this is written in the combination of psi and phi. You can also write it in the form of phi and psi respectively. So it depends on which angle you are writing first. If I have represented it in the form of psi and phi, these are the symbols, that is positive and negative, signifying the values of psi and phi. Now you can see what are the actual values from this particular plot, but since this is not drawn to scale, we need to go through the actual values, and the actual values will be presented to you in the form of a table in the next page. Well, yes, now we have it. For all the secondary structures, we have the values of psi and phi respectively. Now, if we talk about the beta pleated sheets, well, beta or beta, if you say beta in Hindi, it is referred to as sun. Now, beta or sun is going to college and he looks right, left and right. This is one trick to remember these structures like in order. And what you see here for beta pleated sheets, there can be anti-parallel ones and there can be parallel beta sheets. For anti-parallel, you will have psi value as plus 135 degree, phi value as minus 139 degree. It's just similar. It's almost similar, almost in the range. One is positive, one is negative. Then for parallel beta sheets, it's slightly lower, like at least 20, 22 lower. So yes, you can just subtract 20, 20, and what you get here is, like here you have to add 20 and here you have to subtract 20, obviously. You subtract 20 here, add 20 here, and you get plus 113 degree here, minus 119 degree here. Then for collagen, what you can see here is you again have a plus minus combination here, since it is found in the upper left quadrant. So here it is plus 153 degree and it is minus 51 degree. It is exactly like if you divide it by 3, you will get this value. And also you can say that collagen is a triple helix. So yes, this is how you can remember. So this is 3 times. This is 3 times of 51. As simple as that. Moving forward, right-handed alpha helix. Well, you can remember it as 1947 and 1857. Both the years are very important for India's freedom struggle, right? So yes, so this is how we got independence in 1947, but the first freedom struggle 1857. This is the way of remembering it. 47, 57. Well, for right-handed alpha helix, the values are in minus because obviously it lies in the lower left quadrant, and that's why the values are negative. Similarly, for left-handed, it is positive because it is in the upper right quadrant. So it is plus 47 degree for left-handed alpha helix and plus 57 degree phi value for left-handed alpha helix. Now coming to right-handed 310 helix. For it, we have minus 26 degree for psi. The psi value is minus 26 degree and the phi value is minus 49 degree. Then for 2.27 ribbon, well, these are slightly uncommon, generally not mentioned, but yes, if you are making this table, try to make it complete as possible. So for 2.27 ribbon, the psi value is plus 59 degree and the phi value is minus 78 degree. Similarly, for the right-handed pi helices, it is minus 70 degree for psi and minus 57 degree for phi. And that's all about the discussion of Ramachandran plot, the different angles, psi and phi dihedral angle values for various secondary structures. Well, we'll be looking at each of these secondary structures in some other lecture, but as of now, this is the broad concept of peptide bond and the different angles possible, and overall the concept of Ramachandran plot. I hope you have now learned how to draw the Ramachandran plot, how to relate it, how to remember the structures, how to remember the values, and that's all. That's how you can actually answer different questions in various exams. So I hope you have understood this concept very well. Please let me know your feedback in the comment section below. Also, share this video with your friends so that they can benefit from this free initiative as well. Thank you so much for watching. Do like this video if you actually gained some important knowledge through it. See you in the next video. Thank you so much for watching.